In this video, I'll be teaching you guys about resistors in parallel. So there's a lot of similarities between resistors in parallel and resistors in series, but essentially there's just small, tiny differences, details that make it different. So, a resistor in parallel. What is a resistor in parallel? Well, a resistor is in parallel. I just said that like 4 times. Resistors in parallel is if those two resistors share the same node. Okay? So these two resistors share the same node, correct? This entire top section would be a node since this is all a connection point between all the resistors. It's like a similar connection point between all the resistors, and all this entire bottom part is also a node as well. Or it can be at least considered a node. So this resistor is connected to this node, this resistor is connected to this node, and the other sides of the resistors are connected to the same nodes. Therefore, these resistors are in parallel. So the only condition for resistors to be in parallel is if they are connected, both ends of the resistors are connected to the same nodes. All right, and it's going to be pretty obvious on the circuit diagram because they're literally going to be in parallel. All right, what's another thing about resistors in parallel that you need to know? Well, resistors in parallel have equivalent voltages. So if you ever have resistors in parallel, all the voltages will be the same. The reason why, or all the voltages will be the same only if the positive and negative ends are oriented the same way, which I don't know why it wouldn't, but basically if you do KVL in all of these loops, well, you're going to get that this is, let's call this VS. VS will be equal to V1 if you KVL around this loop. If you KVL around this loop and KVL around this loop, V1 will be equal to V2 and V2 will be equal to V3. Alright, so all of the voltages in resistors in parallel are the same. Now the currents, they aren't. And just like for resistors in series, you have something called current division. So you can find the current at any of the resistors. You can find the current at any of the resistors using current division. And current division is like so. So I of N is equal to I of S times Req over R of N. So R of N and I of N, all of them are corresponding resistor and currents. So if you wanted to find the current at, let's say, resistor of 3 ohms, then this would be 3 ohms, and you would find the current at this 3 ohm resistor here. But you need a resistance equivalent. So again, just like series resistors, you can add all these resistors, but you add them in a different way. Okay? So when you add them, you must add them like so. So 1 over R1 plus 1 over R2 dot 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 plus 1 over Req, 1 over Rn, sorry, R of N, N just stands for any amount of resistors, is equal to 1 over Req. And keep in mind, it's 1 over Req. It doesn't equal 1, it doesn't equal Req. All these fractions added together doesn't equal Req. It's equal to 1 over Req. So the math is a little more complicated than series circuits. It's adding now. You have to add all these fractions together. So let's give you an example of this. Oh, my eraser is super tiny right now. So an example would be, let's erase the current division for now. Example would be, so you had a voltage source, and you had these two resistors in parallel. And this one was 2 ohms, and this one is 3 ohms. Well, you would add 1 over 2 plus 1 over 3 equal to 1 over Req. Alright, so what's 1 over 2 plus 1 over 3? So 1 over 2 is, plus 1 over 3 is, so this is 3 over 6 plus 2 over 6, which is equal to 5 over 6. Keep in mind, 5 over 6 is equal to 1 over Req. Alright, so in order to find Req, you just need to find the reciprocal of both of these fractions. So you can kind of flip both of these fractions over, so you get 6 over 5 is equal to Req over 1. And Req over 1 is just Req. So the resistance equivalent here is 6 over 5 ohms for both of these resistors added together. And once you do that, you can represent your circuit as simply one resistor with one singular resistance, 6 ohms. So these two are equivalent to each other. Anything past these two terminals at these green points, your electricity, you will see all of it the same. Now, there's a very useful formula that you guys can use. So, resistors, let's actually keep that formula right there. So adding all the resistors to get resistance equivalent looks like this. Right? But there's something easy that you can do. Well, if you have only two resistors, and this will be very helpful when you're talking about phasor domain and learning about complex math. So when you have two singular resistors, you have 1 over R1 plus 1 over R2 is equal to 1 over REQ. Well, what you can actually do is multiply each of these by R over 2 times R over 2, and this one by R over 1 over R over 1, so that you get the same denominators. And once you get the same denominators, you get R over 2 times R over 2, R over 2 over R over 2 times R of 1, and R of 1 over, let's make that look better, R of 1 over R over 2 times R of 1 is equal to 1 over REQ. Alright, and you can actually add these two fractions together, so you get R of 2 plus R of 1 is equal to R of 2 over, sorry, not equal to, over R of 2 times R of 1 is equal to 1 over REQ. And remember, in order to isolate REQ, you just need to flip these fractions over. So take the reciprocals of both of them, you get R over 2 times R of 1 over R over 2 over R of 2 plus R of 1 is equal to REQ. So if you have two resistors, this is a shortcut formula that I can use, and it's actually very, very helpful in the future, and well, it'll save time on exams too, other than adding fractions. You can just add the whole numbers together. So keep this formula in mind, but this right here is the general formula, and you can kind of derive this formula from the general one. Let's go ahead and solve this circuit. First thing that we can do is, well, we know that these resistors are in parallel, right? They all share the same nodes. And also this voltage source is also in parallel with these resistors. Therefore, if we use KVL around all of these loops, we don't even have to use KVL. But if we use KVL around all these loops, we know that all the voltages are equal to each other. It's equal to V1 and equal to V2. So all the voltages are 120 volts. Alright, what's next? Well, 120 volts is at a resistor, correct? Well, we can use Ohm's law then. So 120 volts divided by 3 ohms should equal the current at this resistor. So this is 120 volts. This is 120 volts. So we can find the current at this I1 resistor by dividing 120 by 3. This is 40 amps. If something's 40 amps, do not touch it. So 40 amps. And how about for this resistor? Well, I of 2 is 120 volts divided by 6 ohms. So 6 ohms is your resistance there. Therefore, 120 divided by 6 is 20 amps. So this right here is 20 amps. All right. Well, we need to solve for I of S as well. Right? This is the current coming from the source. So what we actually realize is since this entire, let's use a different color, since the entire top section is a node, looky what we have here. We could do KCL. So you have a current going in, and you have two currents going out. I of 1 and I of 2 are going out, but I of S is going in. So if we set up the KCL equation, we get I of S is equal to I of 1 plus I of 2. Here's the thing about I of 1 and I of 2. We solve for them. 40 amps plus 20 amps is equal to 60 amps. Therefore, I of S coming from the source is 60 amps. So 60 amps. And that's really all that you need to do for this. But let's go ahead and use current division for one of them to show you how you can actually use it. So what was the formula for current division again? Formula for current division is I of N is equal to I of S times REQ over R of N. Well, what we can do is first find REQ. REQ is calculated by, well, since there's two resistors here, we can use the shortcut method. R of 1 times R of 2 over R of 1 plus R of 2. Ugh. Oh my god, I just got hiccups. Oh my goodness. Oh, that hurts. Okay. Well, if we set up this equation, we'll just get 3 times 6 over 3 plus 6, which is equal to 18 over 9, which is equal to 2 ohms. So 2 ohms is the equivalent resistance. So if we want to find I of N, we need to multiply I of S, the current coming from the source, which is 60 amps, by Req, 2 ohms, over R of N. And R of N, in this case, let's go ahead and try to find I of 1. So the resistance at I of 1 is 3 ohms. So we get 60 times 2 over 3, which is simply 40 amps. So this 40 amps that we calculated using current division matches with the 40 amps that we calculated using Ohm's law. And if you did the same for this other current using current division, you would get the same thing. Well, for this problem, we aren't given any voltages. Now, this looks more like something that would be on an exam. If they gave you the voltage of the voltage source, it'd be significantly easier to just solve for the rest of everything. Like, you saw how easy last problem was. All you needed to do was just get all the voltages and use Ohm's law for everything, and then KCL at the end. But for this one, you don't get any voltage at the beginning. You just get a simple current. So, how do you solve for this? Well, first things first, there's a couple methods that you can use, but one of them is finding the resistance equivalent first. So I can find the resistance equivalent, and then I can use Ohm's law to find the voltage. Or I can use current division. Both methods work, and I'll show you both of them. But first off, go ahead and add all these resistances together. So 1 over 2 plus 1 over 2 plus 1 over 3 plus 1 over 6 is equal to the equivalent resistance, correct? This is the formula to how to find equivalent resistance. Add all the reciprocals of all the resistances. All right, once we have this, we need to put everything so that they have the same denominator. 3 over 6, 3 over 6, 2 over 6 plus 1 over 6. Well, what do we get? Well, add all these together, and you get a simple, let's see, 9 over 6, which is equal to 1 over Req. But 9 over 6 can be simplified into 3 over 2. Okay. So if we flip over everything, use the reciprocal, find the reciprocal of both sides, Req is equal to 2 over 3 ohms. So that's what the equivalent resistance is. Therefore, we can just represent this circuit as one resistor of 2 ohms with an equivalent voltage drop and an equivalent current. That equivalent current should be our 30 amps. Equivalent current is just the total current going throughout the systems at all times. All right. Well, what do we have here? Well, as I've said, since now our resistor in parallel is represented by just a single resistor, we just have a kind of a series circuit, so to say. That means the current for I of S is equal to current at IEQ. Well, now that we have that, that means that IEQ is equal to 30, use a better color, 30 amps. So if we use just plain old Ohm's law, 30 amps times 2 over 3 ohms is equal to 20 volts. So VEQ is equal to 20 volts. Now remember, every single voltage in a resistor in parallel are equal to the same thing. So everything here is 20 volts. All right, how do we solve the individual currents at each resistor? Well, you can use Ohm's law on everything. So you can do 20 divided by 2 here to get 20 divided by 2 to get 10 amps here. 10 amps here. You can do 20 divided by 2 again to get 10 amps here. 20 volts divided by 3 ohms to get 20 over 3 ohms. And 20 divided by 6 to get 10 over 3 ohms. Why am I saying ohms? It's amps. What in the world? 10 over 3 amps. There you go. But instead of finding instead of doing all of that, finding all the voltage and everything, all we need is the resistance equivalent to use current division. So current division was I of N is equal to I of S times Req over R of N. Let's go ahead and test out this theory. I of N is equal to I of S. Well, I of S, the source of your current, or the current going into the current circuit, is 30 amps. And Req we calculated was 2 over 3 ohms. and the resistor that we want to find the current at, let's use 2 in this case, 2 ohms. So all we really get is 30 amps times 1 over 3 ohms if I simplify this, and 30 times 1 over 3 is equal to 10 amps. Therefore, current division works here. So the answer we got from Ohm's law and the answer we got from current division, both are equal to each other. Let's go ahead and do this problem. Well, while I was drawing this, I like how it progressively gets thinner as I draw the circuit. I don't think I'm that good at drawing straight lines. I could use the straight line tool, though, if I wanted to. That may be a good idea next time. But, anyways, first things first. Okay, you guys pick the path. Oh, you picked current division first? Okay, let's use current division. So, I of n is equal to I of s times Req over R of n. Well, first things first, we need to find Req, right? So, how do you find Req? Just add all the reciprocals of each resistor in parallel. So, 1 over 15 plus 1 over 10 plus 1 over 3, and this is equal to 2 over 30 plus 3 over 30 plus 10 over 30, which is equal to 15 over 30, which is equal to 1/2. Now remember, this 1/2 is equal to 1 over Req. So if we find the reciprocal of everything, so take the reciprocal of both sides of this, you flip them over, so you get 2 ohms is equal to Req. Okay, let's move this down. So we have the equivalent resistance right over here. Maybe I should circle the ohms instead of the variable. But we still need to do current division. Let's go ahead and plug in everything. I of n, let's go ahead and try to solve I of 1 in this case. So I of 1 is equal to I of s, 10 amps. That's the current going into the system via this current source, times Req, equivalent resistance is 2 ohms, and 15 ohms is the resistor we want to find the current at. So once we simplify everything here, we get 20 ohms over 20 over 15, which is equal to 4 over 3 amps. So this right here is 4 over 3 amps. All right, let's go ahead and solve I of 2. I of 2 is equal to, again, the current going into the circuit times the equivalent resistance over the resistor we want to solve for the resistance of the current we want to solve. So 10 ohms is the resistance at I of 2. This just equals a simple 2 amps. What about I of 3? Well, I of 3 is equal to, again, I of s, 10 amps, times equivalent resistance over 3. So this is equal to 20 over 3 amps. But we can also solve for this a different way. If we rewrite our circuit with the equivalent resistance, so it looks like this. Our current source is still feeding in 10 amps. We just have a single resistor of 2 ohms. Keep that in mind. And this resistor has a voltage equivalent. So, and it also has a current equivalent. But since this is kind of now a series circuit, it's a simplified parallel circuit. Let's not call it a series circuit. It's a simplified parallel circuit. We have 10 amps going into this node, and then just one single current going out. So this is, the currents will equal each other. So this is also equal to 10 amps. So 10 divided by 2 ohms. Oh, sorry, Ohm's law, not 10 divided by 2. Ohm's law for this is 10 amps times 2 ohms is equal to 20 volts. So every single voltage here is 20 volts. And if you realize, we have 20 divided by 15, that's 4 over 3. 20 divided by 10, that's 2. And 20 divided by 3 is 20 over 3 for the current. So I just use Ohm's law for everything here. 20 divided by 15 gives you current, right? 20 volts. Volts divided by ohms, that gives you current. And we got the same answers we got with all the current divisions. So current division, good in some cases. Finding equivalent resistance, good in some cases as well. All right, you pick and choose. It's really up to you. But as always, if you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thank you for watching.